Hi, I am Dr. G. Srinivasu, Associate Professor, Department of Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. So in the present video, I would like to discuss the surface integral, which is the part of the vector integration. In the previous videos, we have seen the line integral, how to evaluate the line integral, and how to find the work done by force vector F bar, and how to find the flow by using the fluid velocity vector V bar. We have seen several things. Now in this video, I would like to present my lecture on surface integrals. So what is surface integral? So first the definition is, suppose let F bar be any continuous vector point function defined over a smooth surface, R bar is equal to F bar of u comma v. Let S be the region of the surface. Let S be the region of the surface. The surface may be like this. So I can write like this. This is any surface. Let S be the region of the surface. Divide the region into m subregions. Clearly this is first region, second region, third region, so on. M regions whose area is delta A1, delta A2 or delta S1, delta S2, so on, delta SM. So this is the mth surface, small rectangle, this area. Let Pi be any point in the, let Pi be any point of delta Si, and Ni bar is the unit outward normal vector to delta Si at the point P. This is Ni bar or Ni cap. Ni means it is the outward normal vector to the surface. Suppose if phi is any surface, then grad phi denotes that the normal vector to the surface. Then unit outward normal vector will be obtained by grad phi by magnitude of grad phi. This is the normal vector to the surface, and I divide the total surface into m subregions whose areas is delta S1, delta S2, so on, delta Sm. And also I am assuming that Pi be any point in the ith or nth subregion, or Pi means a delta Si is the corresponding subregion, and Ni bar is the unit outward normal vector to delta Si at the point Pi. And let us assume that delta Ai be the vector area of delta Si. Vector area means it is delta Si into, that means what is delta Ai bar is equal to Ni bar into delta Si. So already here delta Ai bar, delta S is the normal area of the surface, and Ni bar with respect to the vector, this is called the vector area. Vector area is obtained by using Ni bar into delta Si. So once again I will explain. Let F bar be any continuous vector point function defined over the smooth curve. This is the smooth surface. This is the surface. Clearly this is the surface. You can write like this. There you can divide the total region into m subregions, and whose areas are delta S1, delta S2, so on, delta Sm. And let us assume that ith subregion, consider the ith subregion, whose area is delta Si, and the unit outward normal vector is Ni bar. Then the vectorial area delta A bar is equal to Ni bar into delta Si. Now, consider the sum. Summation F bar into F bar dot delta Ai bar. Delta A bar is the vectorial area and of the ith subregion, and F bar be the vector point function which is defined on the surface from I is equal to 1 to M. That means for the total surface, I am dividing the total region into m subregions, 1, 2, 3, so on, m subregions. I am considering the sum. The sum is the F bar dot product with the delta Ai bar, where F bar is the function, vector point function defined on the surface, and delta Ai bar is the outward, the vectorial area which is obtained by delta Si into A, Ni cap. or Ni bar, delta Si into Ni bar. So this is delta Ai bar, vectorial area, or I can write this as Ni bar into delta Si. So now this sum as m tending to infinity. Suppose if m as m tending to infinity, and these values will become shrink, these areas will shrink, and this value area delta Si shrink to a point, and the value almost will become 0. Suppose if the n value, n means number, m means number of rectangles, m is the number of regions divided the total surface. Suppose if m is tending to infinity, that means what? The total value, the total delta Si will become 0. Delta Si means it is the area of the ith subregion. So when you divide, the number of points are infinity, delta Si tends to 0, and if the limit is exists, then it is called the normal surface integral of f bar over the region S. So the limit of this sum as m tending to infinity exists is called the double integral. So we write the surface integral as integral f bar dot dA bar, or we can write dA bar is the vectorial area, that it can be written as n bar into ds. So this is nothing but double integral f bar into dot n bar into dx into integral over s f bar dot n bar into ds. So this is area, means there exist two limits. One is length limit and one is breadth limit. So how to evaluate this f bar dot n bar into ds, or f bar dot dA bar? This is the integral over s f bar dot dA bar. This is called the surface integral over the surface S. This vectorial area dA bar can be written as n bar into ds. And now the question is how to evaluate this integral. How to evaluate this integral? So that will explain. So here I want to explain, but I will go to the next slide. So in this I already explained f bar dot n bar into ds. So how to evaluate? So f bar dot n bar. Suppose if you take the Cartesian form, let f bar is equal to f1 I bar plus f2 j bar plus f3 k bar, where f1, f2, f3 are continuous and differentiable functions of x, y, z, then integral f bar dot n bar into ds is equal to, so how you can write f bar is f1 I bar plus f2 j bar plus f3 k bar, the dot product with n bar into dx into dy by magnitude of n cap dot, suppose if it is dx dy, it will be k bar, or we can write it as f1 dy dz plus f2 dz dx plus f3 dx dy. So I will explain now. It is, let R1 be the projection. How to calculate this double integral? This is the main important here, because we are evaluating so many surface areas under the given region. So how to find the surface area? Just you see this. This is the surface S. This is the total surface S. This is x, y, z, or x, y, z axis. And suppose if you want to evaluate the double integral over the region S, f bar dot n cap into ds, or n cap or n bar, both are same. I can call it as n cap or n bar. So n cap is the unit outward normal vector to the surface, and ds is the area of the surface, and f bar small area, and f bar is the function, vector point function, which is defined on the given surface. So this can be evaluated on considering the projection on one of the three planes. So this is xy plane, this is xy plane, and what we call this is yz plane, and this is zx plane, and this is in the space S surface. Suppose if you consider the projection of this surface on xy plane, and this will be a two-dimensional object, am I right? Suppose if you consider the projection of this on xy plane like this, or you can consider the projection in yz plane also, or you can consider the projection in zx plane also. The first note is, let R1 be the projection of S in xy plane. Projection means it is looks like a shade. Suppose if the projection of this is on xy plane, then how to find the integral f bar dot n cap into ds? So then integral over s f bar dot n cap ds is equal to f bar dot n cap, and there are two limits, because length is, suppose if you assume x, then width will be y. So then you will get a dx into dy by magnitude of n cap dot k bar. Suppose if it is in xy plane, so the k bar is the Z coefficient. Xi bar plus Yj bar plus Zk bar means K bar is the Z coefficient. So K bar you have to write. Suppose if it is a dx dz or dy dz, dx dz then it will be J bar, and dy dz means it will be I bar. So in that way, suppose this is xy plane, here there is a z plane coefficient. So if suppose if it is yz plane, then it is I bar. If it is xz plane, this is z bar, J bar. So this is the, if you consider the projection of the surface S in xy plane, then integral f bar dot n cap into ds is equal to double integral over the region R1 f bar dot n cap by n cap dot k bar into dx into dy. Suppose if we consider the projection in yz plane, yz means this is, yz means what it will get, n f bar dot n bar into ds is equal to double integral over the region R2. Let us assume that the region is R2, it is R1 and it is R3, backside. So this is in xz plane. So if we consider the projection in xy plane, I already have written. If the projection is in yz plane means there exists a dy into dz. And here f bar dot n bar is common, and ds what you can write, dy into dz by magnitude of n bar dot I bar. That is the formula. If you consider the projection on yz plane, then the length and breadth limits will becomes y and z. So double integral f bar dot n bar as it is by n bar dot I bar magnitude value of dy dz. Suppose if you consider the projection in the same way in xz plane, then double integral over R3 f bar dot n bar by n bar dot j bar into dx into dz. So these are the different formulas for considering the given surface on xy plane or yz plane or zx plane. So just my dear students, just keep this formula in mind, because we don't have the proof for this formula. Just I have given the explanation for this. So to find the integral f bar dot n cap into dx, you can consider the projection of the surface in any one of the three planes, either in xy or in yz or zx. If we consider in xy plane, that is region is taken as R1. If we consider the projection in yz plane, the region is considered as R2. If the region projection is considered in xz plane, then it is R3. So in the first case, if you consider the projection in xy plane, integral f bar dot n cap into ds will become double integral over R1 f bar dot n cap by n cap dot k bar by into of dx into dy. If you consider the projection in R2 means yz plane, f bar dot n cap into dy into dz by n bar dot I bar. So you can find the symmetry of the formula, so you can remember easily. So this is the way of finding the surface integral in vectors, right? So now, what is the physical interpretation of the surface integral? So that I will see in the slides. What is the physical interpretation of the vector integration? So that is especially it is the surface integrals. So the surface integral of a vector point function f bar expresses the normal flux through a surface. Suppose if it is like this, the normal flux means you'll get like this, the normal flux, or I can show that. So then by diagram, this is normal flux means, suppose if you write like this, this is called the normal flux. The normal flux, it is a curvy linear curve. So this is x, y, z. So the surface integral of a vector point function f bar expresses the normal flux through a surface. That is, if f bar represents the velocity vector of a fluid, then another example, if f bar represents a velocity vector of a fluid, so fluid is a liquid, it is a velocity vector, then the surface integral over s f bar dot n cap into ds over the closed surface s represents the rate of outflow of fluid through the surface. The rate of outflow of fluid through the surface. So suppose if the flux f bar across every closed surface S in the region is 0, then f bar is said to be solenoidal vector point function. So that is another observation or another remark to remember. So the physical interpretation is the surface integral of a vector point function f bar is the normal flux through a surface. Normal flux. Suppose if f bar represents velocity vector, then it is the rate of outflow of fluid through the surface. So if it is 0, on every closed surface S in the region is 0, then the vector point function is said to be a solenoidal vector point function. So that is the physical interpretation of the surface integral. So we have seen the definition. So I will go through the definition. So let f bar be any continuous vector point function defined over the surface, smooth surface. Let S be the region of the surface. So first divide the total region into m subregions and whose areas is delta S1, delta S2, so on, delta Sm. And let us assume that Pi be any point in the ith subregion whose area is delta Si and whose vectorial area is delta Ai bar. So delta Ai bar is nothing but Ni bar. Ni bar means what we call it as unit normal vector to the surface at Pi, at the point Pi at the point delta Si surface area. Then the surface integral is integral f bar dot dA bar or f bar dot n bar into ds. So I will go to some examples so that we can solve the problems. What is the way of giving the problem in examination? So evaluate integral f bar dot n cap into ds. N cap or n bar. So both are same. N bar means what? Outward normal vector to the surface S. And what is f bar? F bar is the given vector point function which is defined on the surface. So evaluate f bar dot n cap into ds, where f bar is a given a vector point function and S is the part of the surface of the plane. So what is here? The plane is given as, so I will write the plane equation 2x plus 3y plus 6z is equal to 12. Or you can write this plane is x by 6 plus y by 4 plus z by 2 is equal to 1. So the plane is x-intercept is 6, 0, 0 and y-intercept 0, 4, 0 and z-intercept 0, 0, 2. So the plane equation is like this. This is three-dimensional x-axis and this is y, this is z. So on arranging this plane like this, so this is the surface. This is the surface. Now we need to find out and it is containing in the first octant only. First octant means that is the eighth part of the total surface. So clearly it is the in xyz first axis octant it is already. So we have to find the integral f bar dot n bar into ds. So already f bar is given. N bar, how to find n bar is the unit outward normal vector. Already surface is given. This is surface. Let it is phi. This is surface is phi. Then find grad phi. So if you find grad phi, what you will get? The normal vector to the surface. Then find grad phi by magnitude of grad phi. That will give unit normal vector. That is n bar. Clear? So you have to write the given phi. What is phi? 2x plus 3y plus 6z minus 12 with a given surface. So then the normal to the plane is given by grad phi. We need to find grad phi. So already we have seen in the first vector differentiation topic, gradient phi, that is indicates the normal vector to the surface. So we need n cap is the normal unit outward normal vector. So first we have to find the normal vector. So normal vector can be calculated by assuming grad phi. So grad phi means I bar dou phi by dou x plus j bar dou phi by dou y plus k bar dou phi by dou z. That is I bar into, I can calculate here, dou phi by dou x. Dou phi by dou x, this is y term, z term constant. Dou z by dou x means only 2. So the value is 2I bar plus j bar into dou phi by dou y. Only 3 you will get. Plus k bar into dou by dou z of this one. 6. So the value is 2I bar plus 3j bar plus 6k bar. What this is? The normal vector to the surface. Normal vector to the surface. Then we need to find unit normal vector. Unit normal vector is denoted by, this is normal vector. Unit normal vector is denoted by n cap. Generally we use the notation n bar is the normal vector, n cap is the unit outward normal vector. But in the given standard book it is given n bar is the unit outward normal vector. So that I am following. So just because it is the prescribed rule. So n cap or n bar. So what is n bar is grad phi by magnitude of grad phi. That is 2i bar plus 3j bar plus 6k bar by magnitude of grad phi. That is square root of 2 square 4 plus 3 square 9 plus 6 square 36. So what you will get? 36 plus 4 40 49. That is equal to 7. That will come in the denominator. So this is the unit outward normal vector, that is n bar. So we reached n bar. Already f bar is there. Then we need to consider the projection in xy plane or yz plane or zx plane. I hope this is clear, all of you. Now, therefore, unit normal vector n bar is equal to this one. Now, I am assuming R be the projection of the surface on xy plane. This is the given, looks like a tetrahedron. Looks like a tetrahedron. Suppose if you consider it is the corner of the room, and if you put a slant plate on the room by touching 3 axes at the corner, then the shape will become a tetrahedron. So the normal vector already we have calculated n bar as grad phi by magnitude of grad phi. That is unit outward normal vector. And f bar already we are given f bar is equal to the given vector point function which is defined on the surface. Now I am assuming let R be the projection in xy plane. XY plane projection means this will be like this only, x, y, e, and this projection means z0. So you will get only x and y terms. What is the equation we get? 2x plus 3y is equal to 12. 2x plus 3y is equal to 12 because z is equal to 0. So the given equation, some 2x plus 3y plus 6z is equal to 12. So on xy plane, only x will touch at x6 and y will touch at 4, but there is no z because it is defined in xy plane. So the equation will be 2x plus 3y is equal to 12. So clear? Already we have calculated n bar, that is unit normal vector. F bar is already given in the given problem, which is called the vector point function defined on the surface. And I am assuming to evaluate this integral, I am assuming R be the projection of S on xy plane. Then integral f bar dot n bar ds will become integral f bar dot n bar into dx into dy by magnitude of n bar dot k bar. So what is n bar? This is, I calculate here n bar dot k bar also. So n bar is 2i bar plus 3j bar plus 6k bar by 7 dot product with k bar. So k bar dot k bar 1, k bar dot j bar 0, k bar dot I bar 0. So only you will get 6 by 7. So the denominator value 6 by 7 already we reached. So we know f bar, we know n bar, denominator also 6 by 7, and we have dx into dy. So the next part is just integrating the multiple integrals, just two integral, double integral, how to evaluate, and by considering the limits of the integration. So now go for the next slide. So already f bar dot n cap. So this also calculated. F bar is 18z I bar minus 12j bar plus 3y k bar. F bar dot n bar. F bar is the vector point function defined on the surface. N bar is the unit outward normal vector. Then the dot product will be 18z into 1 by 7 constant. 18z into 2, that is 32z first term. Minus 12 into 3, that is minus 36. Plus 3y into 6, that is equal to 18y. So that is the term we obtain by making dot product of the two vectors. That is 6 by 7. I am taking out 6. 6 is the common factor. I am taking outside 6 by 7 into 6z minus 6 plus 3y. So this is the f bar dot n cap. Now n bar dot k bar. N bar dot k bar already we have calculated. N bar dot k bar is equal to, already in the previous slide we have calculated n bar k bar is e dot k bar is equal to 6 by 7. So our all requirement is over. Now to find the limits of the integration. How to find the limits of the integration? Because we are considering in xy plane, so there will be the x limit and y limit. So one is constant limit and other one is variable limit. So this is x-intercept 6 as per the given problem and y-intercept is equal to 4. So now on considering the strip inside the region. So already we have seen in the multiple integrals how to evaluate the double integral. And on x-axis y0, this is x-axis and this is y-axis. On x-axis y0, to this variable curve y is equal to, so what value we have to give? Y is equal to 12 minus 2x by 3. 12 minus 2x by 3. So this is on putting z0, you will get R of xy plane. So y value 3y is equal to 12 minus 2x and y is equal to 12 minus 2x by 3. So that is y limit. Y limit y varies from 0 to 12 minus 2x by 3. Then what is the x limit? X limit is the constant limit. It has to vary from this point to this point. That is, x varies from 0 to 6. So these are the limits for integration for the final case. So now, so the limits are x 0 to 6. Here I have given x 0 to 6. Y varies from 0 to 12 minus 2x by 3. 0 to 12 minus 2x by 3 and x varies from 0 to 6. Now the surface integral is integral f bar dot n bar into ds is equal to double integral over r f bar dot n bar dx dy by magnitude of n bar dot k bar. So just to substitute one by one, already I have calculated all the terms in the double integral. F bar dot n bar. So that is 6 by 7 into 6z minus 6 plus 3y. Already we have calculated and I will show this is 6 by 7 into 6z minus 6 plus 3y. This is the top part. And denominator already evaluated, that is also 6 by 7 into dx into dy is as it is. And here x varies from 0 to 6 already as per the given values and y varies from 0 to 12 minus 2x by 3. So double integral over r, 6 by 7 gets cancelled. And what you will get? 6z minus 6 plus 3y. But z is equal to, what is z? Z means what? So 3y, 2x plus 3y plus 6z is equal to 12. Or 6z is equal to 12 minus 2x minus 3y. Am I right? 6z is equal to, so here I am writing, here I am simplifying 6z. 6z means 12 minus 2x minus 3y minus 6 plus 3y dx dy. So I have missed one step. So by rewriting, this is 3y cancel. 3y gets cancelled. Already here written. 12 minus 6 minus 2x dx dy over the region of. So now the final stage of the problem is just substitute the limits, apply the limits and do the integration. Now integral over r 6 minus 2x dx dy is equal to integral 0 to 6, this is x limit, and y limit is 0 to 12 minus 2x by 3. Because it is pure function of x, you can write outside. So integral dy means y, integral dy, integral 0 to 12 minus 2x by 3 dy. That means integral dy y 0 to 12 minus 2x by 3 or 12 minus 2x by 3 minus 0. 12 minus 2x by 3 minus 0 of dx. Or you can take outside 2 already there and here write 3 outside. And in the numerator you can take out 2 also. In 12 minus 2x you can take out 2. So then 4 by 3 integral 0 to x, 0 to 6, 3 minus x into 12 minus 2x into dx. So now on integration means 4 by 3. I'll do this 0 to 6. So 3 12s are 36 minus 3 2s are 6x minus 12x plus 2x square of dx. So what is the integration? 4 by 3 integral 0 to 6 minus 2x square minus 18x plus 36 of dx. So on integrating 4 by 3, 2x cubed by 3 minus 18x square by 2 plus 6x between 0 and 6. That is 4 by 3 into 2 by 3 into 216 minus 9 into 36 plus 36. So lower limit is 0. X 0, this is 0, this is 0. So what is the value? 9 into 36. 4 by 3 into So what this is, LCM is 3 and 216, that is what 532, sorry 432 minus 36 into 9. 324 into 3 plus 36 into 3. So multiplying and simplifying, you'll get the value is equal to 24. Just substitute the value. Simplify and write the value that is equal to 24. So to find the surface integral, we have formula integral f bar dot n bar ds is equal to double integral f bar dot n bar into dx into dy by magnitude of n cap into k bar. So this is the formula by considering the projection in xy plane. Similarly, you can consider the projection in yz plane or zx plane also. So the similar problem, I'll do another integral f bar dot then n bar ds. This also bar dot n cap into ds, or where f bar is equal to this one, and as this is the surface x square plus y square is equal to 16, included in the first octant between z is equal to 0 to. So what is the x square plus y square is equal to 16? So this is a circle equation. x0, suppose if you consider it is xy, then x0 to x square plus y square is equal to 16. It looks like a circle equation having center 0, 0 and radius is equal to 4 units. But here z is a variable factor, z is 0 to, z0 means xy plane. On xy plane z0, 0 to 5, z is upper limit, z is equal to 5. On xy plane z is equal to 0 and in the first quadrant. So first octant means what we will get, I will show the figure. This is the first octant figure. So we are going to find out the surface area of this z0 to 5. In xy plane, this is xy plane. This is z is equal to 0, 0, 5. This is z0 to 5. And here the first octant means it is the 8th part of the octant. 8th part of the total surface area. The total area is this is. So this is the total. This is the total. This is the total because the circle is base and the height is varying from z is equal to 0 to 5. That means you will get a cylinder, right, circular cylinder. So on considering the octant, you will get this shape. This is called the octant. Octant means only 8 part. This is the full region. So now to find the surface integral, already f bar is given that f bar is zi bar plus xj bar minus 3 y square z into k bar. This is the given vector point function f bar. That is okay. Surface is given. Surface means what? 5. So 5 means x square plus y square minus 16. So with the help of 5, we need to calculate n bar. So n bar, how you can calculate? Grad phi by magnitude of grad phi. Already we have done in the previous problem. So this is phi. So first you need to find grad phi. The grad phi indicates the normal vector to the surface. So this is I bar dou phi by dou x plus j bar dou phi by dou y plus k bar dou phi by dou z. That is equal to I bar into dou phi by dou x. Dou phi by dou x what? 2x only, 2x I bar. Dou phi by dou y, 2y. So 2y into j bar. Dou phi by dou z, 0, that is 0. So plus 0. So what you will get? 2x into I bar plus 2y into j bar. This is the unit. Grad phi means normal vector to the surface. Then what is the unit normal vector? N bar. N bar, how it will get? Grad phi by magnitude of grad phi. That is 2x I bar plus 2yj bar by square root of x square plus y square. So this is x square plus y square. So that is equal to 2 into, so 2 into, so 2 already there, here 2 take out 2 value, 2 right outside. So 2 into root of x square plus y square. That is 2 into xi bar plus yj bar by root x square plus y square. That is root 16. Root 16 means that is equal to So here right it is. So let R be the projection of S on YZ plane. Let R be the projection of S on YZ plane. Then integral f bar dot n cap into dx is equal to ds is equal to integral over S f bar dot n bar into, if you consider the projection in YZ plane, this is X, this is Y, this is Z. So the region will be, the region of the surface is like this. This is octet. If you consider the projection in YZ plane, you are considering the projection in YZ plane. So if you consider the projection in YZ plane, it will be a rectangle. So both are constant limits. So I will do the cross section. This is Y, this is Z, and this will be like this one. So Y and Z are constant limits. Y varies from 0 to 4 because the circular area, this is circular area. Z 0 to 5. Already given that Z 0 to Z is equal to 5. And but Y varies from Y0 to Y is equal to, circular area means it what you will get? Circle x square plus y square is equal to 16. So circle with radius 4 units. So Z varies from 0 to 5 and Y varies from 0 to 4. So limits are also known limits. F bar is given and n bar already we have calculated. N bar is equal to 1 by 4 into xz plus xy. This is f bar dot n cap. So on multiplying, this is an n bar dot I bar is equal to x by 4. So already all values are obtained. Just we need to integrate integral f bar dot n bar into ds over s is equal to double integral over s f bar dot n bar into dy into, because we are considering the surface in YZ plane, the projection in YZ plane. So the formula will be dy into dz by magnitude of n bar dot I bar. So f bar dot n bar is 1 by 4 into xz plus xy dy dz by x by 4. So 4 also gets cancelled. And x on taking out, double integral x on taking out z plus y dy dz by x. And x also gets cancelled. So double integral y plus z dy dz. That is z plus y dy dz. The limits are 0 to 5. Z varies from 0 to 5. Now on integrating, how to integrate y 0 to 4? With respect to z integration first. Z or this is z and this is y. So on integrating z square by 2 plus yz between 0 and 5 of dy. So that is integral 0 to 4. So z square by 2, 25 by 2 plus 5 4s are 20. This is yz. So 5y and lower limit 0 of dy. So this is equal to 25 by 2 into y plus 5 into y square by 2 with respect to y integration 0 to 4. That is 25 by 2 into 4 plus 5 by 2 into 16 and lower limit. So 2 2s are 4. So 25 2s are 50 plus 2 4s are 16, 5 4s are 2 8s are 16, 5 8s are 40. So 50 plus 40 is equal to 90. That is the required solution. Just evaluation. Simplify the problem and get the value that is equal to 90 is the required surface integral calculation value that is equal to 90. So with this I conclude my lecture in this session. So in the next session also we do in the same vector integration surface integrals and we'll solve some more problems on this also. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.